August 4th, 2021, Mathfest. I gave a talk, The Diabolical Denominator. Unfortunately, the slides didn't maximize, so I'm recording this one separately. And you can find copies of the slides just by Googling Shield Mathfest 2021 slides. And within a week or so, I'll have the slides turned into a paper, so you don't have to watch the video. So, the diabolical denominator. Let's try advancing. The choice of the denominator is third on my list of the important questions to ask if you're a decision maker and you want to be statistically literate. The first question is, how big? About a third of the news stories don't give you any size. The second question, compared to what? Oftentimes, the people running the argument pick the basis of the comparison to support their point of view. The third question, per what? That's what this talk is about. I'm saying the choice of the denominator can cause, number one, a change in direction over time in a ratio. Number two, it can change the direction, the relationship, the ordering between group rates. And number three, it can change a difference, a reordering between group prevalences. Now, rates and prevalences, that's a subtle distinction, but you'll see more of this when I get there. The main thing is the choice of the denominator is the user's choice. And that choice can be innocent, it can be naive, but it can be diabolical. It can be evil, wicked, and cruel, and you don't even realize it. Main thing is, denominator choices have statistical consequences. So let's move to some examples. Here we're talking about a denominator choice causing a change in rates over time. In the top table, we're looking at the cost spent, the money spent in the US on microwaves in dollars per year in 1980 versus 1987. Top row of data, per household, the amount increased from 14 to 20, a 43% increase. But the percentage that reported spending money on microwave also increased by a bigger amount. So that when you look at the microwave costs per year, per household reporting, it decreased from 483 to 250. Now, students wonder, how can the same data give different results? Here's a very simple example. Per what? The bottom table, we have babysitting. 1980, 76, 1987, 1980, $76 per household. 1987, $75 per household. It's going down 1%. But the percentage reporting also went down in that period. So that when you look at the babysitting costs in the US per year per household reporting, it went up by 5%. This is not algebra. This is not calculus. This is not statistical randomness. This is per what? Next, the denominator choice causes a change in the comparison of rates. The 1996 auto death rate was 7 times as high in Hawaii as in Arkansas per mile of road. But it was twice as high in Arkansas as in Hawaii per vehicle. Now, what the news people are going to do is just say the auto death rate was 7 times as high in Hawaii as in Arkansas, or it's twice as high in Arkansas as in Hawaii. Both statements are true, but they're ambiguous. They don't tell you per what. Now, I got into this because I was watching a video of President Trump talking with a reporter about COVID death rates. And the reporter was talking about per million population, and Trump was talking about per confirmed cases. That's what generated this presentation. So on the left side here, at the very bottom, we have Michigan with 1,662 deaths per million population. Rhode Island had 2,399. Michigan had fewer COVID deaths as of the 1st of May, 2021, than Rhode Island per million population. But as we move up the pyramid from population to cases to hospitalized to deaths, and we look at it per 1,000 confirmed cases, Michigan had 25 deaths per 1,000 cases. Rhode Island had 20. Now, Rhode Island has a lower COVID death rate than Michigan per case. So Michigan has a higher death rate than Rhode Island per case. Michigan has a lower death rate than Rhode Island per capita. Which one is right? Per case or per capita? Now, as statisticians, we have no expertise in this matter. We're simply showing that there are consequences to choices. Well, maybe it's neither one. Well, what else could it be? Well, we're trying to think of something that's closely related to COVID deaths. Population's a long way away. There's a lot of people in the population that don't have COVID, never got it. And there are people in the case scenario, yeah, they've got COVID, but not everybody got tested. Population's too many, cases is too few. What I really want is infections. Infections. And if we knew what it was per 1,000 infections, that might be a better way to make the comparison. But we don't have it. And so we have to argue, well, which is more closely aligned with the infections? Is it the cases or the population? And this is what you're talking about, giving reasons as to why maybe cases is closer than population. Now, the third item, the denominator choice shows differences in group prevalences. Here I'm not talking about the rate of arrests or the rate of crimes. I'm talking about the prevalence of, on the left side, guys. Let's work on the left side first. In the population, men are about 49%. Among those arrested, men are 73%. And in prison, men are about 93%. Is this a disparity? Well, of course it is. Is this discrimination? In statistical literacy, we say association is not causation. We say disparity is not necessarily discrimination. It may be, but you have to argue for it. So we have a disparity here. 73% of those arrested are men, but only 49% of the population. This is a disparity. Could this criminal justice system be discriminatory against men? Maybe. Now let's look at the right side. Here we're looking at Blacks. Blacks are 13% of the population, 26% of those arrested. Is this a disparity? Absolutely. Is this discrimination? It may be. But just as with the COVID cases, we wonder, is either of these the best denominator? Is there a better denominator that's more closely linked to, let's say, arrests? Well, in the case of COVID, we talked about infections, but we didn't have the data nationally. Here, we do have some data nationally. It's the Bureau of Justice Criminal Victimization Study. We call up people at random and ask if they've been victimized. And we ask, regardless of whether that was reported or not, what was the gender of the person? What was the race of the person that did the victimizing? On the left, according to self-reports, and we've got to be really careful here. People are not great at self-reports. They can forget. They may choose to say something that isn't exactly the truth. But among the males, 49% of the population, 73% of those arrested, according to the self-reports, 75% of the perpetrators were males. And now you're comparing 75% of the crimes committed are committed by males, 73% of the arrests. Now, this doesn't prove that there's not discrimination, but it makes it harder to argue. Makes it harder to argue. And if we're trying to get to the root causes, we might say, well, why are males committing more of the crimes? And we want to get under that. Let's move to the right side. Blacks are 13% of the population, 26% of arrests. Among the victims, what percentage of the perpetrators were Blacks? And the victims are saying 25%. Do I know if the victims are telling the truth? Do I know if they're maybe shading, making up stories? I don't know. But it does make it harder to argue for discrimination. Does it prove that it's not discriminatory? No, it doesn't. Statistics has no expertise in saying whether something is discrimination. Statistics can talk about the statistics and how they can be influenced. In this case, how can they be influenced by the choice of the denominator? So, statistical educators should be offering a course that asserts association is not causation. We all do that. But we do it in one lecture for maybe 5 or 10 minutes with 1 or 2 examples, and that's it. We do never show how the association is not causation in any way that can involve a problem or that you can put on a final, unless you're doing a software-based class. We should be asserting that disparity is not discrimination, not necessarily discrimination. What we need is a course that focuses on the story behind the statistics, emphasizes how a crude association may conceal the real story. And you want to show the students these things without computers. Now, that's a tall order, but it's being done. The University of New Mexico is the world leader, in my opinion, at this point, in offering a confounder-based statistical literacy course. 4 sections. They've got over 70 students enrolled at this point for fall 2021. Look at the description. Participants study social statistics encountered by consumers, not the birthday problem. They investigate the story behind the statistics. They study the influences on social statistics. And then they study the techniques used to control these influences. Strong focus on confounding. Now, I'm saying you should be teaching statistical literacy. Read up on the papers. I recently did an USCOTS talk. Here's an USCOTS paper. Just Google 21 Shield USCOTS, and the paper should pop up. I'll be doing a paper at ASA in 2 weeks on getting the University of New Mexico course as satisfying a core requirement in the Albuquerque University curriculum, getting it to satisfy a general education requirement for the entire state of New Mexico. All the colleges and universities can now offer this course, and it will satisfy a math requirement in general education. Thank you. I hope to hear from you on what you do in this area. I think statistical literacy confounder base is the most important thing going right now. Thank you, and I'll stop recording.